Hello, everyone. Greetings from the University of Illinois at Chicago, and welcome to this week's CDAC webinar. We're pleased that Chemek Dera from the University of Hawaii at Manoa has agreed to give today's talk. Chemek is widely known in the mineral physics community for his work in high-pressure crystallography, where he's made a number of important contributions, both scientific and technical, to studies of the deep earth. I was reminded in looking at his CV that his degrees are in chemistry, both physical and theoretical, which is close to home. And he earned these at Poznan, Poland, focusing on, at that time, crystallography of molecular solids under pressure. He began working at the Carnegie Institution first as a pre-doctoral fellow in 1998 and later as an associate staff member, where he interacted a lot with our group. Chemek moved to Jesse Cars in 2007, had an appointment at UIUC for 2 years before moving to the Hawaii Institute of Geophysics and Planetology at the University of Hawaii at Manoa in 2013. And from 2013 to 2017, Chemek was a partner in CDAC. So we're very pleased today that Chemek will be telling us about new developments in his lab, studying static compression and mechanochemical studies of silicates and oxide minerals. Over to you, Chemek.
Thank you very much, Russ. Thank you for the introduction and thank you for the kind invitation. I definitely am very excited with this opportunity to see the CDAC crowd again. Okay, let's see if I can advance my slide. So I just wanted to connect to the CDAC program. I've definitely benefited from it very significantly. Shortly after I moved to Hawaii 7 years ago, I was accepted as one of the academic partners of the CDAC program, and CDAC funded 2 of my graduate students, Hannah Shelton and Yihu, who now have pretty long ago graduated. One of them, Hannah, now works at Lawrence Livermore National Lab, so I think she's a kind of a poster product of the CDAC program, which was established to train future scientists for the national labs like Lawrence Livermore. And Ihu also has a very nice career. She now works for Canon Medical Research, developing X-ray tomographic methods. What I wanted to talk to you about today is focused mostly on minerals and their transformations in the deep earth. So Earth is a complex and dynamic system. It's a heterogeneous environment with a lot of different materials that make up different layers of the planet. Living on the surface of the Earth, we experience major geologic events such as earthquakes or volcano eruptions, and they certainly have effect on our life and livelihood. On the other hand, our activity on the surface also can significantly affect the stability of the Earth in the long run. So understanding the structure, composition, and properties of the Earth interior offer us a better chance to live in harmony with our planet and understand the impact of both the planet on us and us on the planet. Like Russ mentioned, I'm a high-pressure crystallographer. I use tools such as X-ray diffraction or X-ray spectroscopies or laser spectroscopy to basically study physical and chemical phenomena that Earth-forming minerals undergo as you compress them or as you heat them to temperatures and pressures that resemble what is present at different depths inside our planet. So using these tools, we can address a range of different discontinuous and continuous phenomena like elastic deformation and plastic deformation, structural phase changes, chemical reactions, and so on. And what we do is we try to relate them to these important geological processes, earthquakes, plate tectonics, geodynamo, and so on, to understand how these big phenomena are affected by microscopic changes in minerals at pressure and temperature. I particularly like this picture at the bottom of this presentation because it shows the connection of crystallography to geology. So at the bottom, you have some peaks in a diffraction pattern that tell you a story about how a mineral behaves at pressure. And at the top, you have mountain range, which shows you that in the end, this is somehow related to actual large-scale geological processes. I had, like Russ mentioned, I had the great opportunity to learn my crystallography at the geophysical lab. I spent there 7 very happy years, and I had a pleasure and fortune to work with Charlie Pruitt and Larry Finger and Bob Hazen, Russ, and Dave. So geophysical lab, if you look at the history of development of methods in X-ray crystallography for high pressure experiments, has made very significant contributions. Starting in probably mid-60s, they've worked significantly on automating and optimizing single crystal experiments, and measured most of the available minerals up to pressures of about 10 gigapascals, which was back then the standard for diamond android cells. So my talk today will try to focus a little bit on minerals that are relevant for subduction zones, and that have a chance of experiencing interesting discontinuities that weren't quite understood before, both from the point of view of their structural mechanisms as well as possible implications for subduction zones. So if any of you are not geologists, just to introduce the topic, subduction is the process of interacting of two tectonic plates with each other, where one of the plates that has higher density gets subducted underneath the lighter plate, forming this shape that is shown in the figure on the top right side of this of the slide. So subduction takes place at convergent boundaries of tectonic plates, where the tectonic plates move towards each other. One plate thrusts beneath the other and is forced into the mantle. Oceanic plates, which are higher in density, always subduct. We have a lot of seismic activity and earthquake formation within subduction zones. So understanding of the mechanisms that are responsible for subduction and the discontinuities that happen to mineral behavior as subduction progresses is important for explaining how these earthquakes form. So subduction is a little bit complicated. We have the seismic information about how it happens. From seismic tomography, we can reconstruct the shape of the subduction zones. We can see at what angle subduction takes place and what shape the subducting slab assumes. There are a couple of different scenarios here. You can see this nice cartoon movie on the top, which is from the paper of Roberto Argusta, published in 2009. It shows 2 different scenarios for subduction zones of 2 different ages, where the temperature profiles are different. So you can see that one of them, the one on the left side, penetrates the transition zone, which is this boundary between blue and orange, and goes into the mantle. Whereas the one on the right side is stagnant. It kind of bounces off the transition zone and has a hard time penetrating. So depending on the age of the subduction zones and geographically, we have subduction zones with very different ages and different thermal profiles. We can observe one or the other of these 2 scenarios, or a combination of them as well. So what we will try to do is we'll look at some of the minerals that play significant role in the subduction zones, and we'll try to understand whether the structural phase changes, the changes in the crystallographic arrangement of atoms, can have some influence or some control for the subduction process, and can decide whether or not subduction zones, subducting slabs become stagnant or not. So most of the minerals relevant for the mantle are either silicates or oxides. Earth is a silicate planet, a rocky planet. So in this presentation, I will focus on what silicate minerals do, some of them a specific family. If we want to understand the big discontinuous transformations that silicates undergo inside the Earth interior, we have to understand the crystal chemical trends. So Linus Pauling came up with this table of ionic radii ratios that help us to understand what is the preferred coordination number for a specific ion. For silicon and oxygen, the perfect coordination number at ambient conditions is 4. So in most of the surface silicates and shallow earth interior silicates, silicon assumes a tetrahedral coordination. However, this may not necessarily be true under high pressure. We have a number of phases that are known from their presence on the surface that have silicon in octahedral coordination, and we know that these phases form under significant pressure. So this is a figure that I took from Dan Frost's paper that shows the major mineral phases present at different depths in the earth. And you can see that at shallower depths, the surface is at the top of the picture, and we are going deeper and deeper towards the bottom. We have phases with tetrahedral coordination, like these tetrahedra from quartz. And then at certain depth, we are getting to the regime where octahedral coordination is more preferred. So we know for both minerals and glasses, as well as melts, that there are changes in the preferred or dominating coordination number of silicon that happen as a function of pressure and temperature. This is a figure from a paper by Christelsen-Loop and co-authors, where a compilation of data was presented showing the changes in the silicon-oxygen coordination as a function of pressure for a number of amorphous phases, including silica, glass, basalts, and so on, and melts. So you can see that we are starting at low pressure from 4. 5 is kind of an intermediate region. There's no particular step at 5. And then 6, which is the octahedral coordination for high pressure phases, is a plateau that we reach at pressure of about 25 GPa or so. We know some phases with unusual hypervalent silicon. And by this, I mean different than the 6 coordinated silicon that is present in high density silicates and oxides. One of these phases is, its formula is written here. I don't think it has a mineral name. It was extensively studied about 25 years ago. It's a rare mineral that doesn't, or rare silicate material that doesn't occur in rocks at significant quantities, but it has this unusual property of having one of the silicon atoms in 5 coordinated site. So we have not 4, not 6, but 5 oxygens coordinating this one silicon. The studies of this particular phase were done both with X-rays and with NMR spectroscopy, where Jonathan Stebbins did a lot of very nice work about 20 or so years ago. But we haven't really explored or haven't found too many of phases with similar unusual silicon state in silicates and oxides that we've investigated until fairly recently. So when I moved to Hawaii, I decided to explore pretty systematically a group of minerals that is very relevant for subduction zones. We find a lot of them in subducting slabs, which is the pyroxene family. Pyroxenes belong to chain silicates. You can see the structure of interconnected silicon tetrahedra that you can find in pyroxenes. They can accommodate a lot of different chemistries. This is a compositional phase diagram that shows 3-end members, enstatite, ferrocylite, and wollastonite, which is actually not a pyroxene, but a pyroxenoid. You can see that we have an ability to exchange cations quite significantly and preserve the main structural features of pyroxene. If we put more than 50% calcium, we get to this zone where wollastonite structures are dominant, which means lowering of symmetry and more kinking in the chains, but the general topology of these silicate chains is preserved. So over the last, I don't know, 8 years or so, we've investigated a number of different compositions in this crystallographic system and compositional system. We started with ortho-enstatite, which is an orthorhombic polymorph of MgSiO3. In this compositional phase diagram, compositions below 5% of calcium are typically orthorhombic, and above 5%, between 5 and 50%, are monoclinic. So this was an orthorhombic polymorph. This was work that we did in collaboration with Jay Bass and Jin Zhang, who then was a graduate student of Jay. This was early days of developing this single crystal technique for experiments going beyond 10 gigapascals. But the experiment yielded quite interesting information. This is a diffraction pattern. You can see that because the sample is a single crystal, not powder, the diffraction signal is present in the form of these peaks, spots, rather than Debye Scherrer rings. So the geometric pattern of these spots tells us about symmetry and the unit cell of the crystal. You can see as we increase pressure between more or less 10 and 14 gigapascals, the pattern becomes significantly different. We have additional peaks that form, indicating that the unit cell and symmetry underwent changes. So using the crystallographic software for analyzing the data, we solved the structure of the high pressure phase. We saw that there's a significant change in the kinking angle of the silicate chain, not a change in the coordination number. This phase transition was not known before. It was just a little bit above the threshold of pressure that was comfortable for the classical high pressure single crystal crystallography. So being able to conduct this experiment to slightly higher pressure, we were able to reveal these details. This was also a transition that was predicted by first principle calculations by Sandro Jan and Roman Antonak in 2009. So we were able to reproduce that something that theory predicts really happens in reality. We performed a lot of additional experiments afterwards, changing both the composition along the enstatite ferrosilicate joint, as well as extending the pressure range to much higher pressures. And we discovered that orthopyroxenes go through a series of several phase transitions. The one that we found with Jin and Jay was just the first one that happens just above 10 gigapascals and leads to a monoclinic orthopyroxene. We found additional two-phase changes in enstatite 90 with 10% molar percent iron. And we found that these additional changes change symmetry again from monoclinic to orthorhombic and to another phase group in orthorhombic system. Now, what was interesting is when we solved the structure and refined atomic positions, we observed that enstatite undergoes, or silicon in enstatite undergoes interesting transformations that involve changes in coordination number. So you can see here the low pressure phase with all silicon being 4 coordinated. As we increase pressure to go to the second high pressure phase, one of these tetrahedra turn, and we get a 4+1 coordination where one of the tetrahedra has a fifth bond that is slightly longer than the first 4. And then as we go to higher pressure, one of the chains transforms completely to 6 coordinated, whereas the other one remains in a mixture of 4 and 4+1. So we can see that pressure in this particular system is an easy mechanism, easy tool to adjust coordination number of silicon. All of these phase changes that we found in enstatite are reversible. So when you lower pressure, you get back transformations. The only way to characterize the structure and property of these unusual phases that have these atypical hypervalent silicon coordinations is to do it in situ while the sample is still pressurized. We went to look at compositions with higher calcium content. So this is diopside, which is half calcium and half magnesium. And similar methodology, we put several single crystals in a diamond anvil cell, squeeze them at ambient temperature and observe the changes in diffraction pattern and perform crystallographic refinements that reveal how atoms move, how bonds change. So you can see that in this case, at much higher pressure, at about 50 gigapascals, just like before, we observe a change, additional set of peaks appearing. There's an intermediate state where we have peaks of both the low and high pressure phase present. So there's more peaks in the middle here. And then at about 55 gigapascals, the low pressure phase completely transforms and we only have peaks of the high pressure phase. If you look at what atoms are doing, it's topologically quite similar to what orthopyroxene did. So at about 50 gigapascals, we start from a tetrahedrally coordinated silicon of the low pressure diopside. At about 50 gigapascals, half of our silicon transforms to a 6 coordination, half remains 4 coordinated. So we have a structure where the effective coordination number is 5, but there's no specific silicon surrounded by 5 oxygens. We only have a 4 and a 6 present in the same structure. One of my CDAC students did some more experiments and some computational project in collaboration with Boris Kiefer, and actually observed that there is a sequence of 2 phase changes. The first one was not seen in this first experiment because we increased pressure too fast. But when we looked more carefully, we saw that there was an intermediate 5 coordinated phase that is stable for about 5 gigapascal range of pressures on compression once you pass this region of phase overlap or coexistence of 2 phases. So the mechanism of this transition is again consistent and similar to what we observed for N-statite, and shows that in this particular family, in the family of inosilicates, you can use pressure to reversibly change coordination number and reach coordination states such as 5 coordination for silicon. In our exploration of the chemical complexity of pyroxenes, we also looked at compositions in the pyroxenoid range of this phase diagram. So we looked at wollastonite, which is the calcium end member. The structure here is a little bit lower in symmetry. Wollastonite has several different polymorphs. We focused on the triclinic polymorph, which is called a 1A phase. This is from a paper that was published in 2016 and used Raman spectroscopy. So in this paper, 2 discontinuities in the pressure behavior of Raman modes were reported, but because diffraction was not part of this experiment, the structural mechanism responsible for these 2 discontinuities was not well understood. So our diffraction experiments performed with the same technique by loading multiple single crystals into a diamond anvil cell and collecting single crystal diffraction data, revealed, just like this Raman experiment, 2 discontinuous phase changes. We call these 2 high pressure phases HA and HP. And then if you look at what happens with the crystal structure, the first phase change is just a change in the kinking angle of the tetrahedra, doesn't affect the coordination number. So this is similar to the first phase transition that we observed in orthopyroxene in N-statite. The second phase change, again, analogical to orthopyroxenes, has one of the many symmetry-independent silicon oxygen tetrahedra turn into a 5 coordinated site now. So we have coexistence of 4-fold coordinated silicon and 5 coordinated silicon at this pressure of about 25 gigapascals. If you look at the details of the geometry of this site that becomes 5 coordinated, you can see that it's a distorted trigonal bipyramid. There are a couple of different geometries possible for sites with 5 coordinated silicon. We have the bonds that are out of plane, the apical bonds, a little bit longer than the bonds in the in this central triangular face. So if you look at the different electronic coordinations, configurations of or hybridizations of orbitals for 5 coordinated silicon, you can see that for a tetrahedral silicon, we have an sp3 coordination. This is what is present in most of the ambient phases. If we add 1 oxygen to this mix and arrange it in this trigonal bipyramid configuration, we have sp3d configuration, and then we can add another oxygen, and it leads to an sp3d2 configuration in either octahedral or this pyramidal site. So what we've learned about the behavior of these chain silicates at high pressure is that orthopyroxenes go through a number of structural phase changes that were not known before we conducted these experiments. On compression to 50 gigapascals, they show a complex series of multiple reversible displacive phase transitions. The first of these transformations that happens depending on composition between 7 and 14 gigapascals does not change silicon coordination number. It only affects the kinking of polyhedral chains of silicon. At higher pressures, at 35 gigapascals in ferrosilicate 82, there's another phase transition that now transforms the monoclinic phase to an orthorhombic phase, and thus change the coordination number from 4 to 5, and further at even higher pressure to 6. But this allows us to observe this unusual 5 coordinated hypervalent state. In sodium poor clinopyroxenes, the monoclinic C2/C structure is preserved at ambient temperature to pressures much higher than in orthopyroxenes, pressures of about 40 to 50 gigapascals, above which the structure undergoes a transition involving change in the coordination number of silicon, including 5 coordinated state that we found in gamma diopside. And then in chain silicate polymorph of calcium-rich pyroxenoids, when these are compressed at lower temperatures, they also display a series of displacive transitions, similar to what we found in orthopyroxenes, which at pressures above 20 gigapascals lead to phases with a mixture of 4 and 5 coordinated silicon. None of the observed high pressure penta-coordinated phases in this particular system are quenchable, so they do not provide us with this opportunity to use other spectroscopic techniques that have to be performed at ambient pressures to examine these unusual hypervalent polymers. In terms of implications, the possibility of preserving pyroxenes to beyond their stability field has been explored by Argusta in a couple of papers. And he concluded that such preservation in cold subduction zones can indeed contribute to controlling whether the subducting slab is going to stagnate or penetrate into the lower mantle. So we found additional mechanisms which allow to adjust physical properties and density of silicates in a more gradual way than was known at the time when this paper was published. But the new phases that we have discovered, they haven't been included in geodynamic models yet, so we don't know exactly how this would work. We also don't yet exactly understand the temperature effects on these phase transitions. We've been able to examine them up to about 400 degrees Celsius temperature, but subducting slabs experienced much higher temperatures, up to 1,000. So we still need to extend our studies to much higher temperatures at high pressures. In the second part of this talk, I wanted to show you something a little bit different, definitely out of my comfort zone. So performing these experiments with tiny crystals of silicates in diamond anvil cell, we always dream about being able to make large quantities of high pressure phases so we can perform all these different ambient analytical experiments to learn about the details of physical properties and chemical behavior and so on. So one of the methods that allow to apply dynamic pressure to solid samples, whether they are minerals or inorganics or organics, is a high energy ball milling technique. I'm by no means a discoverer of this technique. This has been around for almost 100 years, I think. If you look at the physics of collision of spheres, and if you could put a piece of sample or pieces of two materials that could react under stress with each other between two spheres that fly at high speed against each other and collide, you can see that first of all, there's quite significant pressure that you can achieve depending on the size of the spheres, their speed, and compressibility. There's also a lot of different mechanisms, a lot of different phenomena that happen during the collision, starting from a simple elastic deformation through plastic deformation, shear, fracture, amorphization, and leading to basically inducing polymorphic phase changes as well as chemical reactions. If you look at the diagram that shows the different strain rates accessible in different experiments and controlling different type of behavior, you can see that the high energy ball milling is gives us access to much higher strain rates that are available in devices such as dynamic diamond anvil cells, not quite as high as gas guns or laser-driven shock experiments, but still it's a very simple experiment where you can work with large quantity of sample. You retrieve all of the sample afterwards, and there's a lot you can do with it, starting from microscopic experiments for chemical analysis and so on. So this slide shows the history of mechanochemistry. It's a figure from a paper by Tan and Garcia, published in 2019. So you can see that mechanochemistry, the ideas of grinding substances together to produce either chemical or physical transformations, it originated actually before Christ and developed over centuries into something that is a fairly well established field, but it hasn't quite spread to some of the areas of material science, and certainly not into geoscience as much as it probably should. Milling devices that can produce these highly energetic collisions of grinding elements are available in different shapes and sizes. This is again a figure from a paper that shows geometries of different grinding mills that are in use and available commercially. So we decided to purchase a couple of different grinding mills. One of them is a planetary mill, the other one is an oscillating mill, and examine whether we could try to induce some of these phase changes or chemical reactions that we are interested in by simply grinding samples at high energy. We decided to test this on a couple of simple systems. We chose two oxides, germanium dioxide and titanium dioxide, as testing systems for inducing polymorphic transformations. And we decided to try our luck at synthesizing olivine in a high energy mill by grinding together two oxides. So if you look at the germanium oxide phase diagram, is very similar to silicon dioxide. We have the same types of phases, at least in the low pressure regime. So we have a quartz type phase that has a 4-coordinated germanium dioxide, 4-coordinated germanium. We have a 6-coordinated phase, which is similar to stishovite. It's the rutile type germanium oxide. We wanted to see if we could start with quartz and by grinding in the high energy mill, transform it to rutile. So from diamond anvil cell experiments under ambient temperature, it was established that the pressure of about 2 gigapascals is needed for this transformation. This was measured in a paper published by Old and Secco some pretty long time ago, where electrical conductivity was measured, and it's actually performed at 144 degrees Celsius. And they found that about 2 gigapascals of pressure were needed to induce this transformation. So we prepared our starting materials, which was germanium dioxide in the quartz phase, commercially available. We used powder diffraction to test that it was pure. It wasn't exactly pure. We had a little bit of elemental germanium that was present in the sample, but it didn't really affect the experiment. We decided to grind it in tungsten carbide grinding jars with tungsten carbide balls, which is the heaviest, the highest density and hardest grinding components that we had available. The grinding was performed in this oscillating mill. The energy is controlled by choosing the frequency of oscillation. We performed this experiment at 30 hertz. And you can see the results. You can see that right after milling for about 60 minutes, about 1 hour, we have first peaks of the high pressure phase of the stishovite phase that form. And eventually, after about 2 hours, the initial phase, the quartz phase, disappears completely. You can monitor the phase fractions of the two phases. So we have quartz and rutile. You can see that quartz goes down with time, rutile goes up with time. This allows to estimate the kinetic parameters of this phase change. You can see that we end up with powders that are milled to really small grain size. So powder diffraction analysis is really easy because you have pretty perfect grain statistics. The grains are fairly spherical and fairly small. The second project we decided to undertake to understand this utility of high energy milling for inducing phase changes was titanium oxide. In this system, we were interested in 3 different polymorphs, anatase, Sri Lankite, and rutile, and which have different densities. We thought that looking at kinetics at the evolution of phase fraction of the 3 phases as a function of the time of milling would be quite interesting. So again, we started with a sample that contained only anatase phase. We performed a milling experiment under similar conditions using the same type of jars and about 3 hours of milling time. And we observed that we first see signatures of the intermediate phase, Sri Lankite, that increases with the duration of the grinding and then starts disappearing with the final phase, the rutile highest density phase forming. We also noticed that if you grind for a long time with at really high energy with tungsten carbide components, you grind off some of the tungsten carbide, which at some in some instances becomes a problem. So again, you can analyze your product pretty nicely. The powder statistics is very good and allows for high quality Rietveld refinement. You can monitor how the phase fractions for each phase develop as a function of time, which allows you for some estimation of the kinetic parameters of this process. So encouraged by these first 2 experiments, we decided to play with chemical reactions. Olivine is one of the principal mineral phases. The best known polymorph, best known composition is forsterite, which is magnesium end member. But that's pretty well explored. We decided to be a little bit more exotic, and in our attempt at inducing chemical reactions by high energy milling, we decided to choose cobalt silicate system. Cobalt silicate with olivine structure is a blue pigment. It has a number of different technological applications. Because of this, there was quite an effort at developing different methods for synthesis. You can use this material in batteries, in solar cells, in a couple of different settings. But quite often in technological applications, the grain size becomes important. So synthesis of nanostructured, nanoparticulate cobalt silicate olivine was of significant interest. So the ball milling method approach seems like a good recipe to make nanocrystalline materials. All of the other methods that were developed successfully before required heating at high temperatures, as high as 1500 Celsius. These two attempts that we made at inducing polymorphic transitions without chemical reactions did not require heating. Just the dynamic shock provided enough of energy to induce the transformations. So I thought maybe this would be a good way to synthesize cobalt olivine at ambient temperature. So in Hawaii, we have a peculiarity. Some of the beaches have green sand, and it's actually olivine. It's just not cobalt olivine, it's magnesium iron normal olivine. The cobalt olivine blue pigment is blue in color, like you can see here. It has the same structure as the normal magnesium olivine forsterite, with cobalt residing in iron sites. So we performed the experiment starting with cobalt 2 oxide and silicon dioxide as our starting materials. We performed grinding under similar conditions to what we used for titanium and germanium oxide. And after grinding for about 3 or so hours, we see that the end product is a blue powder, and analysis of diffraction data after different grinding durations revealed that indeed we can very nicely synthesize olivine structured cobalt silicate by grinding these two oxides, silicon dioxide and cobalt oxide, at ambient temperature. We also analyzed the grain size by looking at the peak widths of the diffraction pattern, and concluded that the average grain size was about 100 nanometers. We performed these experiments in two configurations. We used either the tungsten carbide or stainless steel grinding elements. And in both cases, with the long grinding duration, we noticed that we are grinding off the grinding materials. We are wearing off the jars and the balls. So we had a little bit of iron in the sample that was produced in a steel jar, and a little bit of tungsten carbide in the sample that was milled in a tungsten carbide jar. And we tried annealing the product. We already had the cobalt olivine just after completing the milling experiment. But by annealing, we could make it more crystalline. We could control the grain size better. We could grow the grain size to larger, larger sizes if this was desirable. But what we noticed that because of these impurities, because of having tungsten carbide or iron in our sample, on annealing, we get chemical reactions. So a little bit of our product gets transformed into cobalt tungstate, or in case of presence of iron, we get a little bit of contamination with iron oxide phases, particularly manganite. We performed some TEM experiments to look at the product. So our cobalt olivine is really pure. It doesn't have any other elemental contributions. We have a grain size distribution that is not particularly sharp, but has a peak at about 100 nanometers, and some particles are as small as 20 nanometers. So what we would like to do with this grinding approach to dynamic high pressure experiments in the future is to implement in situ observations. This is work done by Tomislav Friščić, which is really nice. They developed a synchrotron beamline where you can integrate a high energy mill and perform the grinding experiments while collecting X-ray data or X-ray and Raman data from the sample as it's being processed. So this would mean that we can see the progress of these transformations, either phase changes or chemical reactions as they happen during the milling experiment. So this is ongoing. I have this project at Argonne National Lab that is hosted by Jessicars and funded by Compress. It's called Partnership for Extreme Crystallography. These two handsome gentlemen, Dongzhu Zhang and Jingui Zhu, are the beamline scientists, and they are currently working on developing, integrating a high energy mill into our setup that was originally designed and built for performing diamond anvil cell experiments. So this would give us another tool, kind of another dimension to performing these experiments aimed at looking at phase changes or chemical reactions. So to give you my conclusions, in this exploratory attempts, we used high energy ball milling to successfully induce structural transitions to metastable high pressure polymorphs in titanium oxide and germanium oxide, as well as a chemical reaction producing cobalt silicate. One can reach pressures as high as 20 gigapascals in high energy ball mills in certain configurations. This would not be possible in our mill, but it is possible in some other mills. And when one performs these experiments, one has to consider the possibilities of presence of impurities from wear of grinding elements. And these efforts at developing in situ monitoring methodology for high energy ball milling at synchrotron beamlines is being currently developed. Just wanted to show you some pictures of other work that we do without explaining it. We are definitely very interested in energy related topics. We've been involved in research on crystallized ionic liquids and their possible usage for gas storage or purification. We worked on magnetic semiconductors and topological insulators and so on, but that's probably a topic for another story. So just wanted to show my acknowledgements. This was a work involving a lot of collaborators, many CDAC graduate students at other institutions, and I'm certainly very grateful to all the funding agencies that contributed to these studies. Thank you very much.
Thank you, Przemek, for a terrific talk. Nice to have this review as well as to see these great new developments. I wanted to point out something that connects to your theme at the first part of your talk of coordination of oxygen, or silicon by oxygen. And of course, the first clear observation of that was in stishovite, rutile type SiO2. And I was reminded in a conversation with Sergei Stishov over the weekend that it was 60 years ago next Monday that he first observed the diffraction pattern of rutile type SiO2 in experiments he conducted as a graduate student in Moscow. So next Monday, April 19th, should be Stishovite Day, which is—
Oh, that's wonderful. Yeah, thank you for—
3 days before Earth Day.
Yes. Yeah, I also remember your contributions to the Stishovite story. Yeah, it's been a fascinating topic for sure. I think this the 5 coordinated silicon kind of refreshes the field. I think we have by now pretty good understanding of how the 6 coordinated phases work, but in the last 6 years there have been reports of, I don't know, maybe 10 different phases with 5 coordinated silicon. Right. But yeah, seems like an interesting curiosity.
Okay, questions and comments for Przemek. Use the chat. Okay, Brent Foltz has a question or comment. You want to unmute yourself?
Sure. Can you hear me?
Yes.
So ball milling was a real big deal in metallurgy, material science, to make nanoparticles and also amorphous materials. But every talk on ball milling led to questions on how much contamination did you get? What is really the composition? There's a couple of ways around this. I'm glad you're using the tungsten carbide because they tend to be separate chips, so they don't often dissolve as well into your material of interest in your silicates. But did you see this in the TEM work, little tungsten carbide particles in your materials? And also on the steel, did it actually change the iron composition of anything?
Yeah, it's a pretty fascinating topic and definitely something that one has to pay attention to. So my idea was to try to use this ball milling to make synthetic high pressure phases in larger quantities. I thought if I could make stishovite in gram quantities would be pretty nice. But yeah, the contamination by the wear of grinding components is an issue. In this particular systems, tungsten is not really crystallographically compatible with this structure type, so it doesn't go inside olivines or these particular oxides. So we have the EDS data from TM experiments that show that the particles of our oxides and silicates are free of tungsten, but we have chips of tungsten carbide. We've been playing with a couple of different methods for separating the contaminants. One of them is high density liquid separation. So tungsten carbide has a much higher density than most of these materials that we make. You can now work with high density liquids that conveniently go to about a density of 3. So as long as your phases are less dense than 3, that might work, except that pounding these particles together in a high energy mill might cause aggregation that may prevent separation by density. So perhaps combining it with methods like ultrasonic treatment might work better. You're absolutely right about iron. We tried with a couple of different steel grades. I think the wear-resistant steel usually contains chromium, and in our attempts at making this cobalt silicate, we made cobalt silicate with both iron and chromium. So definitely you have diffusion of the element present in the grinding balls into the structure of olive.
As an extreme example, we tried to make nanoparticulate tungsten by ball milling it in iron media. We ended up with a tungsten iron alloy that was about 30 or 40% iron actually after a day of milling. It was amazing.
Very interesting. Yeah, there's a lot of learning and a lot of published material to learn from as well. Yeah, I think there's a progress in the technology of these milling devices. The mill that we have was kind of inexpensive. They make mills that can go to speeds, oscillation speeds, about twice as high, or frequencies as high as what we use. But the grinding off of the grinding elements would become more significant the harder you mill.
It's a great idea, though, to go for high pressure phases this way. That's really interesting. Good luck.
Thank you. We also tried to use this concept of double stage compression. So a lot of experiments, including diamond anvil cells and large volume presses, managed to achieve higher pressures by putting an anvil arrangement inside the high pressure device. So we thought that mixing our sample with something like diamond powder might serve a similar purpose. So you would have these very hard, small crystals of diamonds, being present during collision and pushing even harder on the grains. But it's still underway.
Okay, thanks. I think Paul Asimov was next. Paul, do you want to unmute yourself?
Yeah, I mean, the simplest predictor of how much wear you're going to get in a ball mill is the hardness of the material compared to the hardness of the balls. And at least in the silica system, stishovite is much harder than quartz, right? And so presumably when you synthesize rutile structured GeO2, you're making a really hard thing, which then rapidly increases the wear on the carbide. So I'm not saying it's cheap or easy, but the optimal solution would be to use nano polycrystalline diamond spheres as your grinding medium, rather than putting in diamond powder, which is just going to grind your carbide that much faster.
Sure.
I also wanted to comment to Russ that I was reading Birch 1952, his paper on the structure of the Earth, which in the acknowledgments thanks James B. Thompson for pointing out the possibility of rutile structured silica. in 1952, Thomson had already thought of that.
Yeah, that's actually another piece of the story is that once it was published in the Russian literature, it was Joe Boyd at Carnegie who pointed out to Ed Chow at the USGS that he had made this discovery, and then Ed Chow went and looked at diffraction patterns he had collected earlier from Meteor Crater and found the unidentifiable lines and could immediately ascribe it to Stichevite.
Wonderful. Yeah, it's a great story for sure.
Ross, may I?
Dave Walker was next. Dave, do you want to unmute yourself? He was asking if heating the ball mill would improve yields without increasing contaminant load.
That's definitely one of the directions that is worth exploring. So one of the benefits of this milling approach to synthesis is that it's an ambient temperature process. It's a cold experiment. But I think for many chemical reactions, heating would really work in our favor. The idea that we have is for this in situ experiments at synchrotron, we want to develop grinding jars with windows, optical windows, that would enable either X-ray diffraction or Raman experiments. But we also thought about doing laser heating of the inside of the grinding jar with the heating laser that we have available at the synchrotron. We haven't tried that yet, but that would allow to keep the outside the jar pretty cold at the time when the sample and the grinding balls are hot.
Okay, Valery, you want to ask a question?
Yeah. One more drawback of ball milling is that you, in fact, don't know anything about pressure and plastic strain. So it's a parameter, time is parameter, and also energy, weight of balls, and frequency, which are not physical or technological. And probably the best way to study such mechanochemical reactions and phase transition are in rotational diamond, is in rotational diamond anvil cell. Then you can measure in situ pressure, displacement of particles, and calculate plastic strain. And also in this case, there is no contamination of material from balls, from walls. And the only drawback that, of course, you will not get large amount. But to study, to understand physics and to characterize in terms of pressure and plastic strain, rotational diamond cell much more preferable, I believe.
Yeah, I agree that rotational diamond analysis will definitely have their own unique place in this tool set of high pressure experiments. I think these experiments kind of aim at a different range of conditions. The dynamic effect is one of the unique effects. So what we hope to do, definitely not being able to determine the pressure of collisions is a drawback. There are some theories that take into account these parameters, the shape and size of the grinding jar, the frequency, and the size of balls and everything. And they give you some estimates of the pressure distribution during collisions, but it's also sample dependent. So I think we would need better computational tools for modeling how it works. I also hope that development of these in situ observation methods would allow us to make measurements that would help to estimate pressure, temperature, and strains.
Okay.
More questions? Coming back to silica and ball milling, I had a student many years ago who did a PhD thesis on amorphization of silica, and she got the idea to ball mill quartz to see if we could amorphize it. And it turns out we didn't amorphize it. We turned it into another phase called mogonite.
All right.
And, it's the only way I know you can easily make mogonite, which is one of these metastable phases. It's also one of those poor materials that was once a mineral, but the high priests of mineralogy then excommunicated it from the list of minerals. And because it had such a similar diffraction pattern to quartz. On the other hand, the vibrational spectrum, the Raman spectrum, is completely different. So it is a very different material. It's a nanomaterial. So one of my questions is, are you looking for materials like that? Maybe coming back to Brent's comment, nanomaterials that are, or spaces that are entirely different from what you could make by static compression or dynamic compression in a conventional sense.
Yes, definitely. I mean, I think that the nano regime is one of the natural targets for this kind of experiments. And I think the fact that this compression regime, again, involves formation of defects and a lot of shear, I think it might lead to polymorphs and state that are not normally accessible. I think these are the most interesting. Just for us, it was so far a learning experience. We tried to get some grasp of the controls and you know the main issues with this, but that would definitely be the most interesting direction for the future.
Okay, Peter Pazowski, you have a question? Would you like to?
Yes. Hi, Czemek. Thanks, Russ. And thanks for the great talk. Really impressive results. And I just had a quick question regarding the ball milling process that you showed. I was curious if the lower temperatures that you reach or need to generate these high pressure phases may also reduce the background concentration of color centers or anion vacancies in your recovered materials. And I was curious if you might have seen reports in the literature on luminescence spectroscopy or electron spin resonance spectroscopy to compare the natural material to ball milling material.
It's a very good point. I think this process often leads to unusual optical properties or spectroscopic properties of the milled materials. We haven't tried this kind of characterization with the samples that we produced so far. So far, because cobalt silicate has some applications in battery technologies, we focus on studying the battery performance of the materials. We haven't tried spectroscopy. But it's a great point. Yeah, I think it's
be fun to follow up sometime. Maybe we'd love to collaborate if you're interested.
Absolutely, it would be great.
Any more questions or comments?
Hi, this is Shu Hua. I have a question. Thank you for this great talk, Dara. So before I ask this question, I would like to know my understanding is right. I'm really interested in the milling method to achieve the high pressure phase. So I'm thinking the factors that trigger the phase transition should be the high temperature at that time when the particles are being grounded. There must be some high temperature at that moment. And then the small size, and then the shear stress. Is that right?
Yes, I think it covers pretty well. Yeah, so I think the whole device, the whole system doesn't heat much, but I think there is a temperature impulse during the collision. So there's very localized heat that can help transformations. And I think if you try to synthesize phases or substances that are not normally quenchable, the induction of defects that might help with it, I think. So sometimes defective phases that are normally not quenchable become quenchable.
Okay, I see. So I wonder if we can still achieve such a phase transition by using DAC. For example, we just heat the sample with high temperature and then try to make the shear stress as much as possible, without trying to guarantee the hydrostatic status.
Sure. So I think Valeri's recipe was pretty good. In this rotational diamond anvil cell, you have pretty precise control of the shear component. So you can basically dial it or you can measure it exactly. In diamond anvil cells, by not using a hydrostatic pressure medium, you know that you have shear stress, but it's hard to gauge it. It's hard to understand what is the extent of this shear stress. I think it's fairly easy to measure things like gradient of pressure, but understanding shear stresses is a little bit harder.
I see. Sorry. Thank you. Thank you.
Thank you.
Okay, thank you. Well, thanks a lot Chemik, for a great talk. I'm glad you left room for discussion because there was a lot of interest. So we'll see you all next time. Thank you again.
It was a pleasure. Thank you very much.